Hey there, welcome back. And today we're going to prepare for what's coming on Monday. That's tomorrow. We're going to be talking about electric potential, and that's going to be part one out of three that we're going to be doing on electric potential. So, if you recall, the electrical force on a given charge due to an electric field E, and I say here another Q because it could be that this electric field is generated by some other charge. And in fact, it will be generated by some other charge, not this one. That force is given by this formula. So if somebody gives you the field experienced by a point charge Q, as you see here, then you can calculate the force, the electrical force due to that field on this charge, and that is given by this formula. So F is Q times E. That's very, very simple. But of course, somebody has to give you the field at that point, and then the magnitude of that charge and the sign of that charge as well. And as you know, if this charge is positive, then the electrical force is going to be to the right. And if the charge is negative, the electrical force is going to be to the left. So all this is going to be very important for today. Once you have a force, you can calculate the work due to that electrical force on that particular charge. So if this charge is moving in this direction, then and the force is also in that direction, then the work will be positive. And if the opposite happens, where the force is to the left, but the charge moves to the right, then the work is negative. And so the work turns out it then is determined by the force by delta x, and so the force can be written as Q times E. And so again, depending on the direction of motion and the sign of the charge and so on, then this work may be positive or negative, as written here. So depending on the motion of the charge, this work may increase or decrease the kinetic energy of the particle Q. In other words, the electrical force may be helping the particle move faster or maybe taking energy from it and making it move more slowly. And so you see here something that you're familiar with from the context of gravity. So when you're throwing a rock upwards, then eventually it stops. So the kinetic energy transforms into gravitational energy. And similarly, when you drop a rock from some height, then it accelerates going downwards. And so you add kinetic energy to it at the cost of paying some potential energy. So you go from high potential to low potential. So that's no different here, except that here you have to consider also you have negative charges. And so for that reason, it makes sense also to consider the work per unit charge. And so the work per unit charge with a minus sign in front is what we call the electric potential. And so we're going to see that for a point charge, that work is our electrical constant that we saw before times the charge in question divided by the distance to the point of interest. So this delta V will depend on which points you're looking at. And this delta V is in particular with the convention that the potential goes to zero at infinity. And we're going to be talking about that as well. So something that's going to come up during this lecture and in future lectures is this rectangle here with four different quantities that are all connected to each other. So to a given force, in particular an electric force, there's an energy associated with it. And we usually, or here we're going to be calling it U. This is the potential energy. And then in the case of electrical forces, the force is related to a particular electrical field. And associated with that field is an electric potential. And from that electric potential, it's possible to obtain the electrical energy as well, just by multiplying by a charge. So all these four quantities are going to play important roles in our discussion of electricity in this coming week. And so keep those in mind: force, energy, electric field, and electric potential. And so once again, just to summarize, a charge moving in an electric field will experience an electrical force and will acquire or lose electrical potential energy and lose or acquire, similarly, kinetic energy, depending on the change in the electric potential and depending on the charge. And so here you see a diagram, and we're going to be seeing many of these diagrams during the lecture, where you see, for example, the positive charge that's moving with the electric field due to that force. That doesn't have to be that way. It could be that a positive charge started with some kinetic energy in that direction, and then it's moving upwards instead. But suppose it's moving downwards like this, then the work will be positive, and you're moving from high potential to low potential, and you're acquiring kinetic energy by paying that loss of potential energy from going from high potential to low potential. And so this case is no different than the one in gravity. So when you consider the positive charge basically falling like this, or being pushed down due to an electrical field, it's very, very similar to the case of gravity. The one that's a little bit more difficult and that you should keep in mind is what happens when you have negative charges experiencing electrical fields. And so in this case, the negative charge will go upwards instead. Yeah, so it's really counterintuitive because the analogy with gravity breaks down. And so here, then the thing to keep in mind is that negative charges go from regions of low potential to regions of high potential. So in other words, it's as if you were saying they fall upwards instead of falling downwards, just by virtue of having a negative sign, or being a negative. So another way to think about this that I like is that you may imagine that this field is generated by a positive charge far out here and a negative charge far out here. And so this charge is being attracted towards that negative charge that is somewhere out there. And the opposite happens here. So this negative charge is being attracted to some positive charge that is out there that is generating this electrical field. So that's one way to think about it as well. No matter what the situation, though, the kinetic energy change plus the potential energy change will always be equal to zero. So in other words, kinetic plus potential is the conserved quantity. And that's about it for this preview. And I will see you tomorrow.